apart, one can be one wavelength longer than the other, and still you would get constructive interference. But if it's 1.5 wavelengths difference in path length, then one would be destructive relative to the other. So one has light and dark bands that go over a wide range here. So how does this help us understand microscopes? Well, let's review for a second the way a microscope is designed. So a microscope takes light from a specimen shown over here, and in this case there's just a single point of light generating a spherical wave. And what the microscope objective does is that point source, which generates a spherical wave that diverges the objective lens, then collects a sub-portion of that spherical wavelet and turns that light into a plane wave. Because a microscope is designed such that the specimen plane is exactly at the focal distance of that lens, so spherical waves turn into plane waves. And those plane waves then travel through the microscope tube until it reaches the tube lens, which is another positive lens, which now takes a plane wave and turns it back. The tube lens does this, turns the plane wave back into a converging spherical wave. And that spherical wave ends up as a point there. And this allows us to ask the following question, which is, for a point object in the focal plane, such as an infinitesimally small fluorescent bead, what is the distribution of light in or near the image plane? How is that point spread? Is it spread, first of all, and if it's spread, what is the function of that spread? How does it end up being a particular distribution? So we're going to go through the same idea of wavelets, but now look at it in this case of a converging spherical wave. We're going to look at that part of the microscope because that is where the interference patterns generate a complicated mix of focus to a point plus light around that point. So this is now beyond the tube lens. The tube lens is shown at the very extreme end of this image. There's a converging spherical wave made up of a bunch of wavelets, and each of those infinite points in the emerging wavefront is acting like its own point source of light, like a Huygens wavelet. That is, each point emits a wavelet sending out light in all directions, and all wavelets from the same wavefront are mutually coherent. They're oscillating in synchrony, and because of that, they can interfere in a fixed way. Therefore, they interfere with each other in a very predictable pattern. So let's start now with just two of those wavelets and arbitrarily pick a position midway between them, where that vertical line is, where the distance d1 and d2 are identical. The distance is the same. Those two waves will both be troughing, peaking, or in between at exactly the same point. And therefore, if you add those two waves together, they're in phase, and you will get constructive interference. In distinction, d1 and d2, slightly lower down on that vertical line, one of those distances is now a half a wavelength longer. The top one, d1, is a half a wavelength longer distance than the bottom one, d2. And so when those two waves reach that point, they're out of phase, exactly half a wavelength out of phase. And if you add up those two sinusoids, further down, now d1 is much longer than d2. In fact, exactly one wavelength longer than d2. If you add up those two waves, you're going to get a full cycle out of phase, but they are peaking at the same point, and that generates constructive interference. And so here is the patterns one sees instantaneously on the top and integrated over time on the bottom. And you can see that the troughs and peaks of interference on the top have all turned now into positives and zeros. There's no negative amplitude. When you square the amplitudes, now everything is positive amplitude or zero. And that interference pattern ends up with a series of bands. So at an instant in time on the top, there's a mesh of dark and bright lines. Detectors, including the eye, however, don't see amplitude. We collect intensity. And intensity is the addition of a full cycle of those wavelets that square the result. And the detective interference pattern now has dark and bright lines. And right in the middle, there's a white line running horizontally, and that is the place where the two wavelets are mutually constructively interference, all the way along that length. The dark areas are destructive interference, the light areas are constructive interference. Okay, so we've dealt with two wavelets. And now I just want to say a little bit about the way microscopes work, in the sense that there's nothing so far in what I've said that would tell you where the image plane for these convergent spherical waves are. There's just a pattern of light and dark bands. You're going to see that this approach, without any extra understanding of ray optics, generates the image plane in a particular plane, largely because that is the one place where all the wavelets can be in phase at the same time. But before talking about that, we have to deal with the fact that microscope objectives come in many flavors. And a particular flavor I want to talk about now is not the difference in magnification, which many beginning microscopists thinks is the most important aspect of an objective. It isn't. What really matters for the quality of an objective and its resolving power is its numerical aperture, NA. And the NA has a weird description. It is the index of refraction of the material between the microscope objective and the slide, which in air would be very close to 1.0. But in water or glycerin or oil, that number could be higher. Times the sine of the half angle between the vertical and the largest deviation of light that can still be collected by the objective. So a low numerical aperture lens is shown in A has a narrow collimated collective light coming off the specimen. So if you have a fluorescent specimen that sends light in all directions, you only collect a small amount with a low numerical aperture lens. A medium numerical aperture lens has a slightly larger collimated lens, and a high numerical aperture lens has the highest collimated. It is a fact, and I'll try to explain why, that the higher the numerical aperture is, the better the resolving power of the microscope. We'll have to go back to that wavelet picture and look at the difference on the top between a high numerical aperture objective and on the bottom a low numerical aperture objective. So in that case, we have a wavelet generating light, and you see you're collecting a greater portion of that spherical wave with the high NA lens. So a larger amount of the light is collected, and that generates a larger, basically a bigger plane wave that then eventually goes to the tube lens, and then from the tube lens it's converted into a convergent spherical wave. So with a high numerical aperture lens, you have more of the spherical wave collected, and so you generate a larger spherical wave going out towards the image plane. With a lower numerical aperture lens, you have a smaller amount of the spherical wave collected, and the edges of that spherical wave are very close together relative to a high numerical aperture lens, where the most extreme parts of the spherical wavelet that's converging are far apart from each other, and that turns out to be the critical feature for resolution, as you'll see. So if we compare the extreme wavelets from a curved spherical wave in a high numerical aperture lens and a low numerical aperture lens, you can see that the effect of that is a different pattern of banding down at this arbitrary position here. There may be the image plane, but there's nothing yet to tell you why, because two wavelengths doesn't focus on an image. So the finest fringes determines the finest detail that can be found in an objective. This is what limits the resolution of the image, how fine that banding pattern is, and that period, that is the distance between the bright and dark areas, is related to the numerical aperture. If the two wavelengths are far apart, then interference allows very high frequency set of dark and light bands. If the two wavelengths are very close together, as in a low numerical aperture lens, then the banding is more spread out, and this limits the finest detail in the image plane. So now let's try to not just look at two wavelengths, but add more and more wavelengths to that convergent spherical wave, and look what happens to the integrated pattern of interference down at a plane that ultimately becomes the image plane. So first, high numerical aperture gives short fringe period, gives narrow fringes, low aperture gives long fringe period, fringes. So now, whatever numerical aperture we have, we're going to have a convergent spherical wave. That's that blue circumference one sees at the top of this image, the two lenses. And now what I'm showing you is the two wavelengths in the middle of the lens, plus one wavelength right in the center. So the three wavelengths are interfering, and we're looking at the pattern that is generated by these three wavelengths after we integrate over wavelength and squares. The recorded intensity is a series of bar patterns. It turns into islands. Instead of that stripes, we now have islands of bright and dark. And at the image plane, which will end up where this line is here, one sees that there is an island of bright right in the center, and that is because at that point there, we're equidistant from those three wavelengths, because that point is the center of a circle for which those three wavelengths are on the circumference of that circle, so they're equidistant from that point. And that is why, that is where the image is focused, through the point in the specimen that's located in the center of the image field. And the brightest light is there because the interference pattern is strongest, because we're in all three wavelengths in phase, they're better than anywhere else. If we look at five wavelengths, just add two more besides the three that I've already talked about. Again, the brightest fringe is at the center of the image plane, because that is the one place that all five are mutually coherent. Everywhere else, some interference in a negative way is destroying the intensity, and all wavelengths are in phase at the center of the image plane, and so that does the brightest area. And you can see as you add more and more contrast enhancement, besides these three bright islands, there are lots of little side lobes that are different. So that's five wavelengths. If we go to nine wavelengths, the image becomes more straightforward in a way. That is the one place, again, where all those wavelengths are in phase, because they're equidistant from each other, is right at that point there. And all the wavelengths are in phase there, and that is the main peak, but there is this set of banding on either side of that point. Now, if we just add all the wavelengths together, this is the point square function. This is going from 9 wavelengths to an infinite number. Let's just go through the shape of this object. Now, all the wavelengths are in phase at the center of the image plane. Light is concentrated in the middle of the image plane. All of the fringes or side lobes progressively dimmer. In fact, you need enhanced intensity to see them, as shown in this very bottom horizontal picture. And most of the light is now seen within a cone. It seems like all the interference has left very little light outside of this converging cone of light that focuses on the specimen and then rediverges. This is an hourglass shape, and that comes about not through ray optics, but just through interference of wavelengths. The ray of the main peak is set by the extreme wavelengths, the two on the two ends of that spherical cap, and that is set by the numerical aperture. So the size of the image for a very small point is related to how far apart those wavelengths are. The farther they are, the more focused this object is, and that's why the numerical aperture is essential. So if we compare the effect of numerical aperture on the point square function with high numerical aperture compared to low numerical aperture, you see a profound difference. With high numerical aperture, there's a wider separation between wavelengths, which is possible because they're far apart. As a result, there's a small central peak, whereas with low numerical aperture, it's only a narrow separation between the wavelengths. It's possible to have a broad central peak and less resolution. So let's now think about this in terms of what the image of a point looks like. So if we focus now not in the axial direction, but looking down on the surface of an image of that point right in the focal plane, the point in the specimen would appear as a small dot. This dot is called an airy disk because if you enhance the contrast, you find that the dot is surrounded by these fainter rings of light, which is the diffraction pattern of the point. This is the point square function in one single plane. Airy is the name of a researcher, I think he was originally an astronomer, who saw airy patterns around stars and understood that this was an artifact of diffraction, not the fact that every star had rings around it. The PSF has a series of concentric rings, and the larger rings have progressively lower, the farther out the rings are progressively lower intensity. And if you have to remember anything in light microscopy in terms of equations, it would be this, that the distance from the center of the airy disk, that center circle, to the first dark ring is 0.61 times the wavelength of the light, lambda, divided by the numerical aperture, or that's 0.61 lambda over NA. If you want to carry around any fact about light microscopes, that's the way we should carry it around, because as you see, that is the resolution limit of the light microscope. 0.61 lambda over NA is the distance from the center to the first dark ring. We can also look at the airy pattern in the, not lateral direction, but in the axial direction, in XZ, X a lateral and Z being the depth plane, and one sees that the airy pattern is now not a circle, but more an ellipse. And again, there are two, if you enhance it, there are two dark spots in that direction, and that's a longer distance. It's determined by another equation, 2 times the index of refraction of the material between the objective and the specimen. So 2 times n times the wavelength divided by NA squared. And for high numerical aperture lenses, this is sometimes around 3 times bigger than the XY resolution. So light microscopes intrinsically have slightly better resolution in the lateral plane than their ability to discriminate from one plane to another in the depth plane. So can we use this to help us understand resolution in line numbers? This 0.61 lambda over NA, the distance between the center and the first star peak. There are, if you think about this, these are the numbers calculated for a high numerical aperture lens, a 1.4 numerical aperture lens with light at 480 nanometers. You can see that the lateral resolution, and I'll explain why it's resolution in a moment, is 225 nanometers, whereas the z-axis resolution is 861 nanometers, not nearly as good. So how close is it possible for 2 point sources to be and still be seen as 2 points? This is basically the question of resolving. If two objects are close and you still believe they're separate objects, then you can resolve them. If they blend together, you can't resolve them. Typically, for example, in 2 point sources, and then moving progressively closer, there they are sitting on top of each other at the bottom, and they're far apart at the top. No one would disagree that they're 2 points at the top. No one would believe that this is 2 points at the bottom. How would we decide that these 2 points are resolvable? This is sometimes known as the Rayleigh criterion. It's an arbitrary criterion. It's not a generally accepted criterion that everyone says tells you the resolution, but most microscopists use the Rayleigh criterion, which is the criterion that is related to 0.61 lambda over NA, that distance. So that distance, as I've mentioned to you already, is the distance between the center of one disk and its first dark ring. And if we look at these traces here, these are these 2 points that are just in the Rayleigh criterion apart. That's 0.61 lambda over NA. The center of this object is sitting right on the first dark ring of that object. If you look down here at a intensity trace, where the first one is at its lowest value, is where the other one is peaking. And at that position, there's maybe a little more than 20% of a dip in intensity between them when you add the 2 intensities. One can also make the Rayleigh criterion in the z-axis, where you go from the center of one to the first dark ring, to its first dark ring, the other object at that distance, and that again gives you a value where they dip about 19%. And these are both related, and this one is related to the other equation that I mentioned, to n lambda over NA squared, whereas this is 0.61 lambda over NA. Now, the value of numerical apertures, it makes those points smaller, so presumably the points would function by being smaller and those objects to be closer together. And here's a classic example. There's a bunch of beads where they've been imaged with a low numerical aperture lens, a medium numerical aperture, and a high numerical aperture lens. There's no difference in magnification, but there's no doubt you see that you have a bunch of individual beads with lots of rings around them, but you still see them as separate. In the medium NA, it's a little harder to do. With the low NA lens, it's just a big blob. You can't actually figure out what you're looking at. I want to just say one last thing, which is important to realize, that if you want to get the resolution out of your light microscope, you not only have to understand what limits it in terms of the diffraction limit, but you have to sample the image at enough frequency that you can see those high frequency details. And this requires you to keep in mind Nyquist's limit. And Nyquist was named after a scientist, Harry Nyquist, who stated that sound must be sampled at least the highest frequency in the sound times 2. So it must be sampled twice the highest frequency to extract all the information from the bandwidth and accurately represent the original acoustic energy. So for example, you can here's frequencies up to 20 kilohertz. So a CD, if you have one, will sample at 44.1 kilohertz, so that you can hear that 20 kilohertz clearly. Phone lines pass frequencies up to 4 kilohertz, so phone companies at 8 kilohertz. So the sampling theorem says, and this is just the Nyquist theorem, a continuous function, for example, some banding pattern in image can be completely represented by a set of equally spaced samples if the samples occur at more than twice the frequency of the highest frequency component of the function. So to capture a function of maximum frequency f, whatever it is, whatever image you're looking at, you must be resolving it. You must be taking samples that are at twice that highest resolution, 2 times that frequency, and this is the Nyquist limit. And down here is just shown why you have to do that. If you have a banding pattern, and that red is sort of an area that's going from light to dark, and you only sample at the resolution limit, so you get 1 sample per wave of a light-dark cycle, you're going to end up with aliasing. You're going to end up with a pattern of light and dark that's going to not be the high frequency. If you want to see that high frequency, you have to have at least 1 sample from each peak and each trough. And I just emphasize this because most microscopists do very well. They get very fancy objectives, and then they fall down on the imaging side. They do not do Nyquist limited imaging. So, for example, if the resolution limit is 0.61 over NA, and you want to see that resolution, you're going to have to sample enough so that there are at least 2 pixels between those 2. So the Nyquist limit